Thanks everybody for having me. I was saying earlier, this is my first time talking about this result all the way through with the gory details hopefully in. It's also my first time giving a talk on Zoom, so I have no idea what's going to happen to the pacing. And please do interrupt me if I'm rushing on ahead or if I skip something that you'd like explained. I suspect that'll be necessary at some point. But all right, so here's an outline, and it's really more a warning than an outline. The first thing I should say is that I'm treating this like a math talk, which is to say that I'm skipping the motivation completely, except for maybe I mentioned at the very end. And then ignoring that bit for a sec, the other thing that I should say is this talk is really going to be a talk in two parts. And the first part is going to be hopefully just sort of a friendly high-level overview, statement of the main results. And then the second part is where we're going to get into the weeds and do a bunch of sort of fiddly algebraic combinatorics-y stuff. And this probably works well as a Zoom talk because if you care about the first part and don't care about the second, which is a totally reasonable position, you can just put me on mute once I get through the first thing and skip the awkwardness of leaving a talk halfway through or anything like that. So that's where we're going. That's what's going to happen, hopefully. And then I want to get through those two parts with some time to spare because there's some open questions at the end that I want to mention because I'd love it if someone else solves them for me. There's a few things here that are annoying to me that I want to mention at the very, very end. So I'll try and get to those too. Okay, so yeah, this talk is about XOR games. It's a type of non-local game. What's a non-local game? Well, to me, I think of a non-local game as something played between a verifier, that's this amorphous blue cloud, and a bunch of players. And it's a way of the verifier of testing the sorts of correlations that the players can produce. So how does this work? And if you know what a non-local game is, this is just for me to show you guys the notation I'll be using for the rest of the talk. Well, in a round of the game, the verifier sends some symbol, some question to each of the players, this AI, BI, CI. The players get their question. They send a response. The reasonable thing to do would be to call the responses X, Y, Z. Because I want to save that notation, we're going to call the responses capital X hat, capital Y hat, capital Z hat. And then, so they send that response back to the verifier. And then the verifier has some function of the responses he received, the questions he sent. And from that, he computes a score. And now the goal of the players is to maximize the score they receive. The catch is that the players know the possible questions, really the possible question vectors that can be sent, so the possible AI, BI, CI combinations. They know this function, this V, but when the game is being played, Alice only knows AI. She doesn't know BI or CI. Bob only knows BI. Charlie only knows CI. So the players have partial information about what's going on during the actual game.
Sorry, question?
Yes.
What is the subscript I doing here?
Good. Yeah, it's to match the notation that we're going to be using later. But if you want to think about it, you could imagine the verifier, the first step is they pick some I between 1 and M. And then that I is a way of indexing the A, the B, and the C.
So it indexes the triples.
Exactly.
Yeah,
exactly.
thanks.
Yeah. Yeah, notation is going to get increasingly more complicated, I'm afraid, just in terms of subscripts and things floating around. I'm trying to keep it not too bad, but yeah. Right. So yeah, the players get their questions, send the response, try and maximize the score V in expectation. And now an XOR game is basically the same setup, except for we just put some restrictions on. So they use A, B's, and C's. I'm just gonna, this isn't a big deal. I just want to make them numbers between 1 and N. Why not? These X, Y's, and Z's become bits. They're either 0 or 1. And this score that the verifier, the scoring function at the end that the verifier uses, has this nice simple form where the verifier just takes the responses, the x, the y, the z. The verifier sums them up and checks if it's equal to this parity bit, which I'm calling SI, which is either 0 or 1. And if it's equal, the players get a score of 1. If it's not equal, they get a score of 0. And there's that I floating around again. So the I indexes the questions and the desired parity bit for a given round of the game. Okay, so that's hopefully somewhat standard, well, not too non-standard notation. Next thing I'm going to say is something that's maybe unique. Well, next thing I'm going to say is something that's a little less standard, and it's useful for this talk, but I won't advertise it beyond that. But so the way that I want to think about the XOR games in this talk is as XOR games are really just testing the satisfiability in some sense of some linear system of equations. So what I mean by that is here you have the XOR game set up. Here you have some linear system of equations taken mod 2. The verifier wants to test the satisfiability of. How can they do that? How does the verifier do that? Is in a round of the game. So first they publish this system of equations. They let the players know about it. And then in a round of the game, they pick some I between 1 and m at random, universally at random, why not? They send the AI, the BI, the CI to the players. The players send the response. And now I'm calling these response bits X sub AI, which you read as the response of player X to question AI. So these are the response bits sent back. And then the verifier just checks whether those responses satisfy the associated clause in the system of equations. So I'll let you stare at that for a second. I think I should. I'll explain in another slide why I actually call this testing the satisfiability, why that makes sense. But I have two great frustrations with this project. One is that the first one we're meeting early on, it's that this double subscript here seems sort of unavoidable. And I just want to say it carefully now so that we're keeping track. It shouldn't matter too much, but it's worth saying. So these AIs, BIs, CIs, they're just integers between 1 and n. So, this is just a system of equations on 3n different variables. X sub I, where I ranges from 1 to n. Y sub I, Z sub I. Or maybe I should call that I prime. And then, so these are between 1 and n. And then this X sub j is just a bit that's either 0 or 1. So hopefully I didn't make that situation more confusing. Hopefully that's okay to people. I guess stop me if I've already managed to confuse you, and otherwise we'll move on. Okay, I'll take the silence as promising. So that's the notation we'll be using. Okay, and so why is this in some sense a test of the satisfiability of that system of equations? Well, I'll talk about this talking about from the point of view of strategies. So what I mean by that is I'll talk about describing strategies the players can use to respond to try and win this game. And we'll start with the classical case. So in the classical case, well, the first observation you can make about the strategy is the players, in the classical case, the players share some randomness, and based on that shared randomness, they decide on a response to the questions asked by the verifier. And the first observation you can make is that with a minimax argument, you can restrict yourself to deterministic strategies. So if the players share some randomness, just pick the random seed that maximizes their score and expectations, hard code that into their strategy, and now you have a deterministic strategy. All right, so if the players are playing this XOR game with a deterministic strategy, all you need to do to specify the strategy is specify these variables, the X sub i's, Y sub i's, J sub i's, which you read as, the response of Alice, Bob, or Charlie to the question I. Oh no, we've made a small notation error here. That should say just J/K/L, not A sub I. So XJ you read as the response of Alice to question J. If Alice is sent integer J, she responds with bit X sub J. And so once you've done that, once you've specified these variables, once you've fixed the strategy, you can see really easily if players win a given round. They just win the round if that variable assignment satisfies the associated clause in the system of equations you use to define the XOR game. And if you know that, then you can also compute their score and expectation. And if you want to maximize their score, which gets you the value, it's just the maximum fraction of satisfiable clauses in the associated system of equations. So I'm sneaking a bunch of notation in here. When I say value, that's the maximum score the players can achieve in expectation. When I say classical value, well, that's if the players have classical resources. So in particular, they don't share an entangled state. And then the point is, once you've written down a system of equations and use that to define your XOR game, well, then the value of that game is just the maximum fraction of satisfiable clauses. And so that's kind of nice in the classical situation. And that's why I talk about the XOR game as testing satisfiability of a system of clauses.
So Adam, to be sure, it can be, and it will be probably often the case, depending on your set of equations, that there are I and j such that, for example, ai is equal to aj for different I and j.
Yes, 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 right. Absolutely. Yeah, that has to happen for it to be an interesting game.
Well, I mean, it could be a simple set of equations, but
yes, yes.
In general, that can happen.
Yeah, absolutely, absolutely.
And Adam?
Yes.
The clauses you consider here, they don't mix variables associated to the three different players, right? Or are you saying that you can also do this for a general set of clauses?
No, that's correct. So really, we're restricting sort of a special type of system of equations.
Okay.
Where each equation is an X type, a Y type, and a Z type.
Right. Thanks.
Yeah. All right. So yeah, good. That's the classical situation. Sounds like you guys are following, which makes me happy. Okay, so let's just hop over to quantum land. And again, I'm going to try and just give sort of the minimal notation required to describe strategies. So to describe, describe player strategies for responding in the quantum case. And the first thing you do is you try and do the same minimax argument, which works. It tells you can de-randomize, and it ends up telling you that instead of having to think about POVMs, you can just think about PVMs. So, you can just think about projective measurements here when you're thinking about the player strategies. Okay, and now how to describe these projective measurements, the strategy in general. You need to talk about the state, psi, that's shared by the players. And then you need to somehow describe their actual measurements. And the language I'm going to use is to talk about these things that I'm calling strategy observables, which just gives you, the observable measured by the player, Alice, Bob, or Charlie, in response to a given question. And the one maybe subtle thing that I've snuck in here, or the one thing that's happened, is we've switched from talking about everything additively to multiplicatively. So an eigenvalue 1 to this strategy observable corresponds to a 0 response, -1 corresponds to a 1 response. If you just multiply the eigenvalues together, it's the same thing as adding the responses mod 2. Oh, yes. If I didn't do that, I actually could have used the same notation. Notice I got rid of the hats here. If I wasn't switching between this additive and this multiplicative notation, this framework would just subsume the classical case, because you could just think of deterministic responses as being, 1-by-1 matrices. So that's kind of a nice feature, that we're maybe doing the right thing. We're just subsuming the classical into this quantum situation. And okay, so these are the strategy observables. There's the shared state. And then there's some constraints that I need to put in these strategy observables to match the quantum situation, or to match the XOR game situation. The first is, I have it here anyways, their eigenvalue is 1 or -1, so these operators square to the identity. And the other thing you have to do is you have to make sure that the players can't talk to each other. And to do that, I just set these strategy intervals to commute with each other. And this line would make sense even if I use the other commutator. But just from here on out, when I write a commutator, I'm going to use the group commutator. So instead of AB minus BA, it's this thing. But you should see that if A and B commute with each other, this thing's the identity. So hopefully that's also okay.
Adam, is the first condition then implied by the second now? If you do this multiplicative commutator? Maybe not.
It shouldn't be, I don't think.
Oh, because you have the inverse. Okay, sorry, never mind.
Yeah. The inverse is there.
Right.
Because of the first condition, this thing just becomes XY.
Okay, yeah, right.
Yeah.
Thanks.
Yeah. Okay. And once you've done all this, you can, there's two statements. The first statement for this talk is more important than the second, so I'll just focus on this. You can talk about the required condition for the players to win around I with probability 1. So once you've specified these x's, these y's, these z's, the state psi, the players win the round with probability 1 if psi is in, well, let's say si is equal to -1 for a second, or si is equal to 0 for a second. The players win the round with probability 1 if psi is in the one eigenspace of this combined product of operators. These things commute with each other, so this product is still a well-defined measurement. And maybe I won't say it, but you can believe me, or hopefully it's okay, that when you switch to additive, from additive to multiplicative, the equivalent of getting an even response is saying that overall you're in the one eigenspace of this combined measurement. And then, if you want an odd response, you're in the -1 eigenspace of this combined measurement. So that's how you read this statement. If you care, which there's lots of good reasons to, for this talk we won't, about figuring out the actual win probability of the players for a given round, it's this slightly messier thing, but still totally fine.
So Adam,
Okay.
a question. You're not using the tensor product structure here?
Yes. We have
Or are you?
no, this setup, we're only hitting the commuting operator value, or we're allowing commuting operator strategies. Yeah, and actually in general, everything that I say about the value, I think I should have subscript CO, but for almost all of this talk, I'm going to be talking about the commuting operator value. And it just so happens that at the end, when I pull out explicit strategies, they're going to be finite dimensional, so we can actually get a tensor product strategy.
Okay, good. Thanks.
Yeah,
Yeah, because for finite dimensional, the commuting and the tensor product are the same.
Yes. But this framework is really, it's hitting the commuting operator.
So in principle, there could not be a quantum strategy for this.
Yes. Yeah, right. Quantum is maybe a stretch of the word.
Okay, thanks.
Yeah, that should say commuting operator. Right. And okay, yeah. So what's the punchline? What's the reason, why does this feel interesting? Well, if you set these restrictions on your operators, you maximize over them to get this thing that's the commuting operator value, you can get a number that's larger than just the max fraction of classically satisfiable clauses. So, your commuting operator value can exceed your classical value. And this is sort of, the first great observation about non-local games, that there's something you can do with quantum mechanics that you can't do classically, some correlations that you can produce. Okay. So that's classical strategies and quantum strategies. I feel like you guys seem with me enough that maybe this isn't necessary, but I just want to give two examples that we know and love written in this slightly different framework. So here's the CHSH game, here's the GHZ game, and I've written, the system of equations that I would use to specify these games in the language that I just described. And then you can stare at these, and at least classically, things are pretty easy to see. For CHSH, there's two players. At most, 3 out of these 4 clauses are satisfiable at any one given time, well, for any variable assignment. So your classical value is 0.75. Your quantum value should not be 0.75. That should be an 8. Apologies. But your quantum value can be higher. Your commuting operator value can be higher. And if you want to specify the commuting operator strategy, well, there's the state. And I can describe these measurement operators if I want to. I didn't because they got a little messy. I'll do it for GHZ. So that's CHSH. Here's GHZ. I think, yeah, again, at most 3 of these 4 equations are satisfiable classically. So your classical value is 0.75. Your commuting operator value is equal to 1. There's a strategy that wins with probability 1. Here's the state you share. Here are the measurement operators. And one thing I'll point out that people don't normally do, but I did here just to really make it clear that these things commute, is I stuck the i's in. So now we really have a tensor product form. And you can see that this x commutes with this y, commutes with this z, and everything squares the identity. So okay, I don't want to spend too long on this, but hopefully that looks right to everybody. Again, except for this 0.75, that should be 0.85. Okay. All right, and now I'm going to do maybe the first new thing, which is I want to take this description of commuting operator strategies with the clauses and the strategy observables, and I want to translate this all to group theoretic language. And what I'm going to do is I'm just going to div a group that encodes these strategy observables. And okay, how do you do this? Well, I give some generators, which are these now lowercase x, y, and z's that satisfy exactly the same relations as these capital X, Y, and Z strategy observables. So, they square the identity, they commute with each other. And that would be a perfectly good group, but we end up needing to keep track of -1s. So the other thing I'm going to put in to my group is this formal variable sigma that you can almost always just freely replace with a -1 in your head. The point is just that there's no -1 in the group structure. So I stick in this variable that's keeping track of it. If you're familiar with William Slofster's work, this sigma is something very analogous to the J in his solution groups. And also I think, hopefully I say this, but so this game group I call G, and it just encodes the strategy observables. Okay, so that's a good way of talking about the observables. Then we need some way of encoding the clauses, of actually describing the game. I do this with the clause group H. So it's a subgroup of G. And what you do is you first take all of the clauses in the system of equations, and you translate that to a word in G. I could read this mapping off to you, but I think you can all see it. Maybe I'll just say that I call this thing, this HI, a clause. And then you define, so you translate each clause in the system of equations, a clause word in G. And then you take the subgroup generated by these clause words. So that gives you a nice, well-defined subgroup of G. And if you want to sort of understand how to read, or what the clause group is, why it matters, this is not quite a formal statement, but if the game has value 1, so if the game has commuting operator value 1, so if there's a perfect commuting operator strategy, then every word in the clause group, if you just translate the x's to capital X's and the sigma to a -1, will give you a product of operators that fixes psi. So a product of operators with psi in the one eigenspace of that product. And that's just because this HI is exactly the thing that I said, psi had to lie in the one eigenspace of if the game had value 1. And then you can take those and multiply them together, and psi still stays in the one eigenspace of those things. So this clause group H is really just keeping track of of all the products of operators that have to fix psi. That's how you read it. Though that statement is only true if the game has a perfect commuting operator strategy. So hopefully game group G, clause group H makes sense. And these are going to be sort of our fundamental group objects. And I'll tell you in a sec our first big theorem, which I could have rewritten it, but it sort of felt more honest to copy paste from the actual paper. So there's the first big theorem as stated in the actual paper. And it tells you that a game has perfect commuting operator value if and only if sigma is not an H, where sigma and H are defined just like I did on the previous slide. And maybe the best way for me to give you intuition about it is just to sketch a proof of it. Both directions are interesting. One direction is more interesting than the other. So let's do the only if direction, which I promise you, once you've, I think there's two negations in here, so it's easy to, every time I do this, I forget whether it's if or only if, but I thought hard about it when I wrote this slide, so hopefully I was right. The only if direction would be telling you that if sigma is an H, the commuting operator value of the game has to be less than 1. And maybe if you remember this intuition I said a second ago about how if the game has commuting operator value 1, everything in H fixes the state psi, makes this proof clear-ish. The point is that, if the game has commuting operator value 1, everything in H has to fix psi. This sigma is really just a -1. So that what I'm saying is that -1, psi lies in the 1 eigenspace of -1. So translating that a little more literally, you're saying that psi equals minus psi, which is a contradiction. That wasn't entirely formal. You can make it entirely formal, but that intuition holds up almost exactly. One other thing that I'll say. Yeah. Okay.
Can I ask a question?
Yes, please.
I'm a little bit confused. You have on the one hand this group, and then G and H, and you have on the other hand the observables.
Yeah.
And now, I thought that you gave us a translation from observables to this group.
Correct.
But how do you go from group to observables?
Good. That's a lovely question, because that's going to be the if. Well, okay.
That's what you're doing here, right? Because you say.
Yeah. Good.
You have a statement about the group, and then it implies something about commuting operators. Not.
Right. Yeah. Let me be careful. So in a sec, I'll give an actual representation that produces the observables from the group. But for this part of the proof, you don't actually need that. You can think about this as just assume there exists a value 1 strategy. So assume that these observables exist. Then for every so you have some observables and you have some group. And now for every clause of this form in this H, I can just define a product of the associated observables, the capital X's, the capital Y's, the capital Z's. And then turn this sigma into a -1. And that product of the observables will fix psi if the game has a value 1 commuting operator strategy. And so then this statement that sigma is an H, also because the group elements, because the observables satisfy the same relations as the group elements, this statement sigma is an H then tells me that I can take a product of these observables that fix psi, multiply them all together, and just get a -1, which is what happens down here.
Okay, I think I understand. Yeah.
So it's almost just
are you more saying that if there is a commuting, I mean, the next part is if there is a commuting operator strategy that achieves 1, then you have that. Then you prove sigma is not in H, and now you say if it isn't 1, then it is in H. That's basically.
Yes.
What you've done, I think.
So I'm saying that if sigma is in H, there can't be a perfect value commuting operator strategy. And it's a proof by contradiction where you.
Yeah. So yeah, I understand that.
Yeah.
And then you don't need the translation the other way.
Right. Yeah. Okay. But now for this direction, we do need a translation, which is to say that now I'm going to say that sigma is not in H, and I want to actually pull out a perfect value commuting operator strategy. And then this, so yeah, I said one direction was more interesting than the other. This direction, really, I'm just sort of, my group is really just keeping track of, my group is almost just keeping track of notation for me. It's keeping track of me multiplying together a bunch of these operators. This direction now, I think is maybe what you were asking about. This direction, I'm saying now sigma is not in H, and I actually claim existence now of some measurement observables. And so to do this, I actually need to construct some strategy observables, these x's, y's, and z's, and I need to do this via, I do this via representation. And I don't want to get, you could do this in more detail, but I'm just going to sort of, I just wanted to give you guys a few key ingredients here. So I do this via representation, and the representation, I just take the left action of the group on I think that's left. Maybe that's, I'm pretty sure that should say left, on left cosets of H. And this is a standard thing. Okay, I'll finish and then I'll make this comment. So I take the left action of the group on left cosets of H. And then once I've done that, I have nice well-defined matrices. I need to pull out an actual state. And this is your state. This is the description of the state psi. And once you've done this, and you have this representation defined, it's not too bad to check that these two conditions hold, which are kind of the key ingredients. That psi acting on this thing, sorry, sigma sends psi to minus psi, and that H fixes psi.
Adam?
Yeah.
Should we think of psi as being an element in what is it called, the group algebra over C? So is this like a formal linear combinations of elements from G with well, I guess in this case they're real coefficients?
Yeah. Let me.
We're using like a permutation representation.
Yeah. So right.
Okay.
Yeah. The reason I'm hesitating slightly is because I think that statement is correct, but if H could be an infinite group, and then if you think of this as sort of a sum of group elements, you have an infinite sum of group elements.
Mm-hmm.
So I'd rather just think of my basis. I'm just going to define a basis that are all the left cosets of H.
Okay.
In G, and then just take the left action of the group elements on this basis. So that so
you're considering the quotient group of G by H.
Yes.
Then?
Yes.
Okay.
Yes. Exactly. Yeah.
Uh-huh.
Yeah. And then these group elements have a well-defined left action on the cosets.
Thanks.
Yeah. Hopefully that sounds good. Right. Okay. The other thing that I should say.
Question:
is that,
would any
go ahead.
Would any representation work?
Would any let's see. The only thing that you have to worry about is you have to worry about pulling out the state psi somehow.
Oh yeah.
Oh
yeah, true.
But yeah, any representation would give you well-defined, I guess, measurement observables.
It gives you unitaries, which are these observables, right? They're unitary.
Yeah.
They're plus one, minus one eigenvalue.
Yes.
They're squared to identity. Yeah.
Yeah. And then so really the only trick here is pulling out the psi in some sense. Okay, and the other thing that I should say is I called this, main theorem sort of boldly. This is not really a new theorem. It's the notation is new, but this is, I think, really just a special case of the GNS representation. You could also get this result just appealing to completeness of NCSOS if you felt like it, if you wanted to. So, I mean, this proof is nice, but I shouldn't, if I'm doing due diligence, I should point out that there's other ways to get this that people sort of always already knew. I think this is, if you squint, just the GNS representation, or something very, very close to it. Okay.
Adam,
sorry.
Yeah. Where it says check, the second thing I'm okay with, but don't immediately see why sigma psi is minus psi.
Yes. Your key detail there is that sigma commutes with everything and squares through the identity.
Okay.
So then, then hopefully you believe that?
Yes.
Okay, yeah.
Thanks.
Welcome. Okay, so right, but this is still I guess the starting point for something interesting, because what have we done? Well, we've taken a problem about matrices or operators, and we've translated it into something purely algebraic. This question, is sigma in H, is an instance of what's called the subgroup membership problem. And I'll just make this point here that, again, if you're familiar with William Slostra's work, this looks a lot like it. He ends up with the word problem. And I guess the one key distinction for our case between the word problem and subgroup membership problem is that this thing H is not a normal subgroup. I'll just explain that briefly. It's not a key point, but if H were a normal subgroup, you could just mod out by H and then ask, is sigma equal to the identity? And that's exactly the word problem. But here, because H is not a normal subgroup, you can't just mod out by it. So you have a slightly different problem. It's the subgroup membership problem. And okay, I'll say this slightly cryptic, but maybe enlightening statement. That corresponds to the fact that there are operator identities that hold acting on the state psi that don't hold in the group. So there are products of operators, psi lies in the one eigenspace of a product of operators. Well, it's not true that product of operators is actually literally equal to the identity. And this is, I think, a phenomenon that happens because we have to consider multiple players at once. I think if you just considered one player as subspace, you could always ignore this, but something like that is true. But I think that statement probably wasn't formally correct. Okay, right, so this is nice. We've turned it into the subgroup membership problem. The unfortunate fact is that the subgroup membership problem on this group can be undecidable. And I don't know, it would have been too much to hope for to get something better than that. I mean, I think almost, most things are undecidable. So that's not too shocking. But the point is that we're not just asking, we haven't just created a general case of the subgroup membership problem. There's a lot of additional structure here in the definition of this group H, in the fact that we're asking not about an arbitrary group element, but we're asking about sigma. So we really care about specific instances of this problem that can be undecidable in general. And well, then the key question is, what can we say about those instances? That's a hard problem. For 2 players, we know that those instances are decidable, and that goes back to Searleson. The result that I'm going to show you guys is that for 3 players, these instances are decidable. And that's where we're going to that's a result we're going to sort of drag kicking and screaming from algebraic combinatorics. I mean, it's with some work that we get this result. And then for more than 3 players, I have no idea. But if I get to it, I will say some vague things about it at the very end of this talk. Okay. I'm not going to get through everything, but that's okay. I'll try and do justice to this stuff at the beginning. Okay, so this was our first big theorem. Now I want to talk to you about sort of our first key idea, which is this thing that I call k-modding. It's a name that stuck by accident. And the point is that instead of asking this question, is sigma in H, which is maybe undecidable, why don't you just take G and mod everything out by some normal subgroup K, and then ask if, the coset, if the element corresponding to sigma is an H mod K. Okay, and now this is sort of a tricky statement, so bear with me. It's a weaker condition, which means that if sigma is an H, then sigma is an H mod K. So if you take that and you translate it, that means if, take the contrapositive of that statement. If sigma is not in H mod K, then sigma is not in H. So by the theorem we just stated, there exists a perfect commuting operator strategy. And the additional detail that you get out of this is that not only is there a perfect commuting operator strategy, you've actually proved something more. You've proved that there's a perfect commuting operator strategy where the operators satisfy some additional relations that are imposed by this group K that you've modded out by. And I'll just say that in the other direction, if sigma is in H mod K, it's this test is inconclusive, but it does tell you that there's no perfect commuting operator strategy where the operators satisfy the additional relations imposed by K. So we can't say anything about the commuting operator value, but you have ruled out commuting operator strategies where the operators satisfy these additional relations that K tells you about. Hopefully, I'm saying relations imposed by K. What I mean is if you mod out by K, I could also just think of adding to my group relations which are the generators of K. So that's why I keep saying relations imposed by K. And maybe an easier way to say this all is if you take a kind of dual to this K modding is to say that instead of searching over all the strategy observables, you place some additional restriction on the strategy observables, and then you search over this restricted set. And if we didn't have all of this algebra language, the natural restriction is to just place a cap on the dimension of the matrices, or the dimension of the space that you're looking at. But this gives us some other nice cap that we can put, which is, well, we can mod out by any relation that we want, and in a sec I'll see that my suggested choice is that we sort of impose some level of nilpotency on the strategy observables, which you'll see in a sec. But hopefully this idea is somewhat friendly. Makes sense to people. There's a couple negations between here and here, but this hopefully makes sense. Okay, all right. And why do you do this?
Still the second bullet problem, right? It doesn't solve it completely.
Yeah. Yes, absolutely, absolutely. Right now it's just, I don't know, maybe a nice algorithm to decide some special cases or something like that. Okay. Right, and okay, yeah. Why do you do this? Because if you pick a nice K, then G mod K has a solvable subgroup membership problem. And you actually get an algorithm that terminates and tells you something, at least. Okay. I wanted to give examples. I think I will rush through this, but let me just, well, I should tell you about two of these. I'll skip the warm up, but let me just say it. If I pick K to be the commutator subgroup of G, and I mod out by that, what I'm really doing is I'm just saying that all of my strategy observables have to compute with each other, which really is just kicking me back to classical strategies. So it's nice. If I mod out by this K, this thing becomes an abelian group. It's solvable, and it makes sense that we're solvable because we're just asking if there's a classical value 1 strategy. So that was going to be the warm up. The K that, for reasons that are still sort of bizarre to me, ends up being interesting, important for our case, is that instead of taking the commutator subgroup of G, so instead of just taking the commutator of all these group elements, take the commutators of pairs. So that's what it looks like. But I guess in words, instead of, oh no, sorry. These should all be X's. These should all be Y's. These should all be Z's. Of course, these things commute with each other already just by the initial definitions. But what's not true is that two pairs of X's don't necessarily commute with two other pairs of X's. But now when I take this, when I mod out by this K, I'm imposing that additional restriction. on my operators, that they pairwise commute. Okay, and I'll skip this. It's not actually a normal subgroup of G, but we just upgrade to even length words and even length products, and we can do this without damaging much. And this is the K. So everywhere else in the talk, when I say K, this is the K that I'm talking about. So earlier I was just using K to be some general normal subgroup. Now this K is the one that we're going to fix from here on out. And there's sort of by lucky accident, some nice things that we know about the type of strategies that you get when you mod out by this K. And this is a result by myself and Aram Harrow, Anna Natarajan, Gurtej Kanwar from a couple of years ago. We didn't use this language at all because we didn't have this K modding language, but this is just a restatement of that result. The first thing tells you that if you mod out by this K, you can check if sigma K is an H. Don't worry about that E. It's just we're switching to even length everything. You can check if sigma K is an H in polynomial time. So you could see that actually you've made the group nilpotent. So you know that there's a polynomial time algorithm. But there's actually quite a nice one. So this is a reasonable K to mod out by. The other thing that's really a lucky accident is that if you mod out by this K, if you mod out by this K and sigma K is not an HE, so you know that there's a value 1 strategy, and you're looking for strategies where the operators satisfy this additional relation, then there's actually a very nice strategy. It's a very nice strategy that's played on a GHZ state, 1 qubit per player, and your measurement observables are actually really nice. They're just Z rotations and X measurements. So this proof I'm not going to talk about. It's given in this old paper in different language, but we sort of stumbled across it by accident. We just wrote down, we talked about these strategies. We wrote down a condition for these strategies to achieve value 1. And then we wrote down, we had this polynomial time algorithm. We got a condition there. And these conditions turned out to be dual to each other. So for our case, the point is that if you mod out by this K and you get a perfect commuting operator strategy, you also have a perfect tensor product strategy. So that's why I think in the abstract I mentioned that we're going to show perfect commuting operator implies perfect tensor product, and that comes from this result here. Okay, and now now here's the final big deal. I've been sort of building up to this. This is the one that's a lot of work to prove, and that's the following statement. That now if you pick the K that we talked about, you pick the H and the G, you take the same framework. One direction of this implication we always knew, but this becomes bidirectional. So instead of asking about the subgroup membership problem in the larger group, you can ask about the subgroup membership problem mod K, and it turns out that that's equivalent. And if you have this theorem in combination with all the other theorems that I stated, you get this nice this chain of equivalences that says if there's commuting operator value 1, well then sigma is an H. This theorem tells me that then sigma is also an H mod K, which then by the theorem on the previous slide tells you that there's 1 qubit tensor product strategy. And this is bidirectional, so it goes the other way as well. So this is quite nice. This was the headline of the talk, that perfect commuting operator for 3XOR also gives you perfect tensor product.
Adam, for which K is this?
Sorry. Yeah, this is for the commutators of pairs.
Okay.
So yeah. the K that says XIXJ commutes with XKXL.
Yeah.
Yeah.
And could you elaborate just for a second on the superscript E? I didn't quite follow what.
Yes.
What that's doing.
Yeah. I tried to sneak this in. So the point is, if you pick that K that says that the pairs commute with each other, You don't, you can't, let's see, what's true. You can always take the normal closure in G, but for some reason you don't want to. You end up wanting to take the normal closure. Instead of talking about G and H as I define them, I restrict myself to a G. Well, I restrict myself to an H, where instead of just taking products of clauses, I take products of pairs of clauses. So I always have even length pairs of clauses. So instead of just having a single HI, I have HI prime, you know. So I always, it turns out that this is totally fine because for these, in order for everything to cancel down, your word needs to have even length anyways. Your operators cancel in pairs. So you can ignore the odd length products of clauses you can toss all those out without tossing out a possible refutation, which is my language for, you know, a product of clauses that's equal to sigma.
Okay.
So that's a sort of technical thing that you end up having to do. What do I want to say? Oh yeah, I don't know how important it is, but I'll tell you that if you want to upgrade to XOR games where you don't query all the players, so you can talk about XOR games where you query a subset of the players and then you ignore some players' responses, then that's the step of this proof that breaks, actually, interestingly enough. Because if you're not querying all the players, then perhaps an odd length sequence of clauses is something that you care about. I mean, that cancels to sigma. I don't know if that's fundamental or just a small trick that needs to be applied or something, but it's interesting.
Would that apply to this small 33111? What's the example called again?
Yeah. I3322.
Right.
It would be close. This whole framework only really talks about value 1.
Mm-hmm.
So
right.
it's hard.
Right.
There's a few other, but yeah, I mean, if you can ignore players, then you get very close to I3322, and it seems interesting, but who knows how interesting.
Yeah. Thanks.
Yeah. Okay. So yeah, this theorem then is the one that's doing the heavy lifting. And it's right. This direction we talked about already. This direction is the hard one. That's some algebraic fuddling. And now, okay. So that's the first part. That was supposed to be the first half of the talk. It's the high level overview. Now, I do want to talk about the end, but I feel like I should let me take 5 minutes to rush through this very, very quickly and just try and say a few key details, and I'll push through some slides pretty fast.
We started a few minutes late, so you can take 10 if you want.
Okay. I think 10 is enough time for me to try and do this somewhat honestly. Okay. But yeah. Okay. This is part 2 of the talk. So this is where I'm now gonna go straight into the weeds and talk about how to prove that final theorem. So okay, if people have questions about the first half, now's a good time to ask them too. If people want to put me on mute, now's a good time to do that. Okay, I'll get into it then. I think maybe the most important thing I can say to you guys is to give you some notation that I think is the right notation. It doesn't show up in the paper just because it's a little hard to tech and you don't need it. But when you're thinking about these things in your head, at least, here's how I suggest you write them. If I have a word W and G, I have this wire notation for talking about it, where, you know, this W1 is the X generators, this is the Ys, this is the Zs. And this makes sense because the X's commute with the Ys commute with the Zs. So this is, you know, a fine way to write it. Where we're going, we don't really need to keep track very often, but if I want to put a sigma, I'll just stick it there to let you know about it. And I need to keep track of what I call empty wires, you know, words where the X part is equal to the identity. And I just do that with this dash on the wire notation. So hopefully that's all okay. The wire notation is sensible. Just if you take a product, you can take a product in each of the wires. This one now is maybe worth staring at. It plays nice with commutators. So if I have the identity on one of my 2 wires and I take the commutator, Well, what ends up getting written here is W1 blank, W1 inverse blank. So I just get the identity. And I pick up commutators on the lower two wires. The other thing that happens is the sigmas, because they commute, they cancel each other out. So this is just, what happens when you stick a word through a commutator represented in this wire notation. Hopefully that's sensible to people.
So the subscripts 1, 2, 3 correspond to X, Y, Z, and so
yeah. So the word W1 is all made up of X's.
Right, and
W2 is all made up of Y's.
The commute that you can you can separate them into 3 blocks.
Exactly.
Okay.
Yeah. I mean, really, I just need different subscripts here because these are different words. But whatever is going on the top wire is X's. Whatever's going on the middle is Y's. Whatever going on the bottom is Z's. Okay, so there's that. There's the commutator. Yeah, okay. I just mentioned those two things. You get the identity, and you cancel out the sigma when you take this commutator. Okay, the other piece of notation that I want to tell you about is this thing that I call the clause graph. So what I want to do, it's a hypergraph. What I want to do is I want to have vertices corresponding to each of the clauses. So all of the X's, all of the Y's, all of the Z's. Here, it ranges from 1 to 6. Here's a set of clauses. We've lost all information about the sigmas in what I'm about to do, but that's okay. And I'm going to draw a hyperedge for each of these clauses. And what you get is this sort of garish looking thing where the colors have no meaning except for I just wanted to distinguish hyperedges, which is hard to do if they're all the same color. And there's just a picture of the clause graph, which is something I'll talk about in a second. It's just a useful visual representation of the clauses in the game. Again, without the sigma information, but that's okay. Okay, so proof, and this is going to be really a proof sketch, but I'll try and say some important things. This is the statement that we want to prove. This is the direction that we want to show. And if we take, if we take, well, yeah, if I take this direction, and I think it's just this direction. If I literally take this direction, another way of saying it is that I have some word in H, which has a sigma on it, and has a W1, W2, has a sigma times some junk, but that junk lives in K. And then from that, I want to clean off all the junk and just say that sigma is in H. That's that's this direction of the proof. And notice that it's equivalent. This is just because of how groups work. Instead of getting sigma in H, I can just say that this thing W1, W2, W3 is in H, and then I can take this, multiply by the inverse of this, and I just get sigma. So that's going to be the framework that the proof takes. We're going to assume existence of this sort of a word in H, and then we're going to show that we can get the same word without a sigma. You'll see what we do exactly. We're gonna invert these guys one by one. First, we're gonna get rid of the W1, then the W2, and then the W3. Okay. So step 1 here is this implication, which I'm gonna use. Notice that if this implication were true, I could take this word, multiply by the inverse of this word, and I've cleared the W1. So I've gotten now a word just with W2, W3, and nothing on the W1 wire. And it's been disguised by the notation and the fact that I've just started talking to you about all of this, but this is not a hard thing to prove. You could sort of prove it to yourself, I think. The point is that if I want to find a word in H that just matches on the top wire, just matches on the X's, well, that's fine. Just pick a clause that matches, just pick a clause that matches on the X's and don't care about the Y's and the Z's. And you've got to have a clause that matches on the X's because you've got those X's from a word in H. There's nothing tricky going on here. And the only important thing is that every time you get an XI, you pick the same clause H. And because the xi's show up in, because this W1 is in K, because this is a commutator, each of the x's show up an even number of times. And so your sigmas just naturally cancel each other out. And I'll give you some, here's the formal version of what I just said. I can define this map, which takes just an x to some clause in H, which may or may not have a sigma. This map, I just pick clauses associated with every x. And then I apply this map, which is actually, it is a homomorphism, to now the whole word W1. And I get something that matches on the x's and has some junk on the y's and the z's. So hopefully you're still with me. Once I've done that, I take this word, multiply this by the inverse of this word, and I've cleared the first wire in this language. Okay, so what's next? Well, I want to clear the second wire, but I want to clear the second wire without introducing any junk on the first. So I need a word that now looks like this in H, that matches on the W2, has nothing on the W1, and has some junk, down here. And I guess let me also say this, this word already would do it, except for this word has a sigma floating around, and I want to leave that sigma there. So I need to find a word that doesn't have the sigma in it. And okay, this I will skip, but the point is that you can construct now a second, you can construct a map that does exactly that. That inverts, sorry, I say inverts because I think of a projection that takes this word to just the W2 element. And then I think of an inverse of it, which gives me something that matches the W2. So I have a map that inverts on the second wire while keeping the first wire the identity whenever possible. And that's this thing. And you can construct it by sort of staring hard at the clause graph. It's not too bad once you have the clause graph defined. I mean, I claim that I guess everything that I've done so far, you could, if instead of me talking to you at it, I just let you sit and think about for, a couple of hours, I promise would seem totally reasonable. Okay, so yeah, I define this map, this homomorphism that does this thing to W2. It inverts W2, leaves the first wire blank, sticks some junk on the bottom, and then I just apply that to W2 to get this word that I care about. And now, okay, let me just talk about clearing the last wire very, very briefly, because this is maybe the important bit for why K matters, why K is sort of interesting. So we ran through it, but the point is after steps 1 and step 2, you're at step 3, that should be a 3, where now you have some word that has a sigma in it. It only has stuff on the bottom wire, and that stuff on the bottom wire is in K. So that stuff on the bottom wire looks like commutators of pairs of clauses. This is sort of the simplest example of a commutator of pairs of clauses down here. Okay, I'm running over time. Let me just say this intuition. Here's what you want to do. I want to say, well, this thing is an H. So this thing is an H, and I already have this map. I skipped the definition that will invert this thing, give me some junk on one wire, but leave the other wire blank. So if I could do that to just one of these two pairs, let's say I could just invert Z1, Z2, put some junk on the second wire, but nothing on the top wire. Okay, sorry, this statement isn't true, but I'm just trying to carry through some intuition here. So this is what I want you to look at. If I could somehow invert this Z1, Z2, leave the top wire the identity, and put some junk on the second wire, and invert the Z3, Z4, leaving the second wire the identity, and put some junk on the top wire, then when I take the commutator everything cancels itself out, and I get exactly what I wanted. So that was fast, but that's, you know, I guess this proof came from starting with this intuition, you know, realizing that the proof didn't quite work. And you can sort of drive yourself crazy doing casework and trying to think of all the ways they can break and checking that all the cases work. And then eventually, the actual proof, we stuck some gadgets in and made the whole thing work. But I think maybe the intuition is more important than the actual mess of that proof for this last step of the result. That when you take these commutators of pairs, you can stick identities on some wires and commute, and you get the identity all the way through. Okay, so I have gone over time. Let me skip this motivation, and let me just end with this pretty picture that hopefully outlines the, you know, what we've done and what's new and what's possibly interesting. It's a picture I've had in my head for a while, and I finally made the graph or the chart. This is supposed to list the possible open questions related to this. And the point is that if you talk about hardness of deciding the value of an XOR game, for 2 players, we know that's easy. That's Zierelson. If you care about the general value for 3 players, and I think for more players, I actually, I hope that's true. There's a nice result by Thomas that tells you that it's at least NP hard to compute the value of the XOR game. But what we've shown in this result is that value 1 3-player XOR games have a sort of special status, where even though saying anything else about the value is NP hard, at least, deciding whether or not the game has value 1 is you can do in polynomial time. And if the game has value 1, you know, there's nice simple tensor product strategies that work. And I have some hope that something like this k-modding trick can get more players, just the value 1 part of it, for more players. And I can, maybe offline, I can say some words about what that might look like. I have hope, but it's also, I think, a very hard problem and a problem to drive yourself crazy thinking about. So I don't suggest it too strongly as a research problem to anybody, but you know, think about it for a couple weeks every 6 months is sort of my policy. Because I do, it seems like something should be possible there. And then the other, you know, sort of family of open problems that I'll talk about is it should be possible to make k-modding play nice with NCSOS and say something about the more general value. And I don't know what that is. You know, you can't say too much because of this NP hardness result, but at least it would be nice to have NCSOS working with this additional restriction placed on the operators, and then maybe, you know, maybe in that case it'll terminate. That's something that I think you could believe is true and might say something interesting. All right, so I am over time, but I will gladly take questions, and I think I'll stop there.